Okay, chapter 13 is surface measurement. Alright, so surface metrology is nothing but we're going to investigate the surfaces by using the instruments. You can also call it measuring the surfaces. It's the same thing, okay? But it's kind of like an inspection actually. And it's an important consideration in manufacturing. We use it all the time. So surface metrology is a concern of many branches of science. It is widely involved in the world of commerce and also manufacturing. So this type of measurement is really important. Also, we have to use instruments that are sophisticated in order for us to be able to inspect the surfaces. So in most situations, surfaces are made to allow the parts to mate effectively with each other. Because when you take a look at this picture, you can see how this equipment is built, okay? And you can see how these two hidden surfaces are mated to each other. And for that to happen in manufacturing, you definitely need to do the surface metrology, okay? Along with surfaces, lubricant speed and interference fits are also considered when male and female parts are pressed together. Okay, every time we manufacture parts, okay, where two surfaces are pressed together, then we call male and female parts, and you will learn that in other courses as well. So right now we're going to concentrate only in metrology measurement. So the surface conditions are measured. We're going to use gauges, and also we're going to use instruments, okay, particular instruments to measure the surfaces. Alright, so this is figure 1-3, okay, behind this, and I cut the top part so you can't see the exaggerated figure. This is showing you the surface texture. It's just a texture chart. Again, this is our standard for metrology ANSI. So here you can see the process, and here you can see the roughness, okay? And this is our micrometers. So that's your mu and an m, so that means micrometer. We also use the micro inches, just in the brackets right here. So now you know that the flame cutting, the roughness is between 25 to 12.5 micrometers. Okay, that's between 1000 to 500 micro inches. Okay, so that's how we take a look at the roughness. Again, surface texture from the ANSI standard. So the background or history of surface metrology was established after the Industrial Revolution, so the importance of surface finish was first called to attention, okay, by this person, R.E. Reason, and he is from the United Kingdom. And the first version of B46.1, that's a standard, and that appeared in 1940, but widely used after 10 years later. Okay. And the first recorded discussion of surface metrology is totally attributed to Leonardo da Vinci. So that's way back in 1452 to 1519. So stage one of the surface metrology history is Leonardo da Vinci. In the 18th century, he started to study actually the surface. Okay. So all contacting surfaces are assumed flat, and then the area of real contact was nearly the same as the apparent areas of the surfaces. So that's what he found out at that time. Okay, so in stage 2 of surface metrology history, so metrologists, they come to recognize the surface of roughness or asperities. Asperities are nothing but just the roughness of your surface, and they also recognize surface roughness as much greater effects on the parts. Okay, when we do manufacturing, the roughness on the surface is going to affect the parts. So we have to really get into the surface in order for the parts to press together or mate together. So the elasticity of a specimen is its stiffness, and then the ability, okay, of the material to resist deformity. So when it is loaded. So being elastic is nothing but being resistant to the deformity when it is forced, okay, by something. Plasticity, okay, plasticity of a specimen is a malleability. So you have to review your chemistry, okay, and the inability of the material, that's the plasticity, okay, is totally inability for the material to resist the deformity. So when it is loaded, so they're kind of opposite to each other. So here you can see the plasticity, and this one is elasticity, okay, ability. So for elasticity, it's going to resist the deformity. For plasticity, it's not going to resist. Okay, they are not able to resist the deformity. Okay, so stage 3. So they discover that load, okay, load is nothing but just the weight of something, and the characteristics of the parts and the lubricants, all of them, okay, affected both elasticity and plasticity. Okay, definitions. The surface metrology or surface topology refers to the geometry, okay, and texture again of surface. If you want to know the texture of a surface, all you have to just feel it, okay, with your hand on the surface. So the condition of the surface is defined by its characteristics. So we have surface texture, and we call that finish. And roundness is a function of your geometry. Material, we have hardness, and we have surface metallurgy. Okay, so ANSI B46.1 is just a standard for geometry and also texture. So here in this picture, you can see 3 forms of asperity came from theoretically normal surface. It looks like a normal surface, but they have some kind of a roughness in there, so we call that asperities. So the roughness, the waviness, and then error, okay, of form. So which all vary according to length of spacing or wavelength. Wavelength is nothing but just a distance, okay. Alright, the fourth asperity or roughness is not distinguished by wavelength. The first 3 we can distinguish by wavelength. So it is just a flaw. Okay, the fourth asperity is a flaw of your surface. And that's not covered by our ANSI standard. So here you can see in this picture the flaw right there on the surface. So error of form, roughness, waviness on the surface, they do not always have the same lay. Lay is nothing but the direction of these asperities. Okay. So again, lay in most cases means roughness, okay, waviness, and that's your asperities, and the direction of the asperities, we call that lay. Okay, that's your term or terminology for the surface metrology. And waviness, roughness and waviness, they may be perpendicular to each other, okay, in some cases. So there are no good or bad surfaces, there is only surface appropriate for the application you want to do on it. So we consider resistant, corrosion, reflective, quality, overall, geometry, metallurgical property, and finish in surfaces. Okay? So those are the properties that we always look at when we study or measure the surfaces, okay, in preparation for manufacturing. So here's just a lay symbol, okay. We have the entire package right here in this table. I'm just going to show you 2 right here in an exaggerated picture. So if you see this little 2 symbol, lay again is the direction of your asperity. So this lay approximately parallel to the line, okay, representing the surface to which the symbol is applied. The example showing the direction of tool maker is this way. And here another one, another symbol for lay. So here that's perpendicular to the line representing the surface to which the symbol is applied. So you can see for toolmaker, we use this kind of signs for him to give direction. And you can read all of that, and you definitely need to know this, and I'll definitely ask you in your assignment. Surface evaluation stylus method. Okay, let's measure the surface. So the most common way done to evaluate surface is to compare it visually and feel it. Okay, so here we can see in this picture showing you using a microscope. And we are evaluating surface, okay, by using the magnification of that microscope, so we can easily compare the surfaces. Even though two surfaces appear to be identical, they are actually different. Okay, none of the surfaces are identical, even though they may appear to be identical. So these are the tricks of science and nature. So we also use interferometry, because that's another method to study or evaluate the surface. Evaluating the surface is the same as measuring the surface. So for practical shop work, we use a stylus instrument to study the surface. So it's the most familiar method for practical shop work, and you can see in many merchants selling that kind of instrument so that you can use it to study any kind of surface. And it best demonstrates the fundamental principles of surface metrology. So even though this is just ANSI standard B46.1 discusses several other methods, alright, the standard is based on the stylus method. So in the instrument, the stylus is drawn across the surface and generates the electrical signals, and they're proportional to the changes in that surface. Then it's going to produce a graph looking like that. Okay, from the data it collected from the surface. So any graph created by stylus does not represent the real surface. Graph will generate exaggerated height, okay, of the asperities in relation to the spacing, and which is known as the distortion ratio. So when we compare the graphs, you look at the distortion ratio, okay, which is right here, and they're not the same. So you can see that's 4,000 divided by 200. That's 4,000 divided by 50. So you can see 250 how different, okay, they are. So here 2 zeros will cancel out, and you have about 20. Here only 1 zero will cancel out, okay, and you have about 80 here. So you can see how complicated they become, okay, as the ratio is going up. Same thing right here. And for you, if you can be able to see and identify this is the magnification ratio, and this is for surface study, and these are our asperities, and they come out from the instrument that we're studying the surface with a little stylus on the surface data. And if you can know about that much, it's okay. You don't have to know how to calculate or how to make the graph at all, okay? You only know and recognize what that is. Alright, the stylus and the datum. So we can see with electron microscope that no surface is perfectly smooth, okay? We use appropriate instruments to study the surface asperities, and there are two types of stylus instruments. The very first one is true datum, also called the skitless instrument. Another one is the surface datum, and we call that the skit type instrument. Skit is just a part of the instrument. So here you can see in figure 13.8 is your true datum stylus instruments, and it's going to move the stylus right here, okay, across the part along a reference datum established by the instrument. So an early true datum instrument is shown in this picture. So with a true datum instrument, we draw across the surface in a very precise, mechanically controlled movement. Okay, now you can see like that. and we access the surface based on the path, alright, of that datum font. So putting here, that's your part, and the part has a surface, and we are studying or investigating that surface by using this little stylus, okay, a part of this true datum instrument. Alright, the stylus and the datum. So surface datum instrument can be set up easily because the surface being accessed is used as the datum. Okay, so here the surface, and we are studying, inspecting the surface of that little part, and we're using that as a datum. Okay, and that's what we call this instrument as a surface datum instrument. A supporting slate, so either this is your supporting slate, and we call that a skid. Okay, sometimes we call this a shoe because it looks like a shoe, and just a resting place for the stylus, because you can't just run the stylus on its own. You have to have a support, okay, to help the stylus to be able to travel on that surface to investigate it. So we need that kind of support, either the skid or the shoe, okay, rests on the surface and slides that stylus. Alright, so typical skids have radii. The skids are looking like a little cylindrical thing, and so they have a radius. So typical skids, okay, they have the radii ranges from like 6.35 millimeter all the way to 50.8 millimeter. So here in this picture, you can see the radii of a skid must be relatively great compared with the feature being accessed, okay. So here the other feature, and here these are your skids. So as the wavelength of the asperity increases, asperity is nothing but the little dents, okay, roughness on the surface. These are very, very exaggerated picture. So what it's trying to tell you is the radius, okay, of this skid got to be bigger than your wavelength of your asperity, okay. So as the wavelength of asperity increases, the skid approaches the stylus in its movement until S and C, they are the same. Okay? So at this point, the asperity to be S's will not appear on the graph at all. As soon as the skid approaches the stylus in its movement until they are the same. Okay? So you're comparing the skid radii and the little, okay, wavelength distance of this asperity. See, these asperities are very small. Now it's growing. Now this is really big, yeah. So when you take a look at this radii, see, they are about the same, okay, with that asperity. It's just a roughness, so when the surface is not straight line, there is a wave right there, and we call that asperity. Okay, to completely assess a surface waviness and primary texture, okay, we have to investigate. So you will investigate waviness, you investigate primary texture in order for you to be able to completely assess your surface. So waviness can occur with the same lay. Lay is the direction of your asperity. So as the primary texture as asperities. Okay, so waviness can happen with the same direction of the pattern as a primary texture as your asperities. So however, in machining, when we do machining, the lay of the waviness can be sometimes perpendicular to your primary texture. Okay? So it's important to choose correct stylus in proper direction of travel when assessing waviness. So most waviness is difficult to see, so there's one test to assess waviness, and it is by using a float boiled stone, and it will usually reveal the causes of waviness. Alright, when the head of the stylus instrument crosses the surface at a uniform speed, it generates and electrical frequency. Okay, and we describe that frequency is equal to speed of traverse divided by your wavelength. This is just a part of your wave. So the amplitude of the waves correspond to the heights of your asperities. Higher frequencies are usually eliminated because we don't want it, and this kind of elimination is called adjustment, and in common word we call that a cutoff. So you know the wavelength, okay, that's the one length of your wave, and then you know the speed of the traverse, you know how the waves are moving, and then we also have the frequency, okay. The frequency we always get by dividing the speed of the traverse by your wavelength. Okay? We're just counting how many of them, how many of these asperities are. Because asperities or roughness usually looks like a wave. So therefore we use the wave equation in order for us to be able to get the frequency, meaning how many of these peaks are. So that's what we're trying to find. And your machine is going to give you this too, okay? And the frequencies of the peaks that you see on your graph, yeah? So that's how you connect everything. So make sure you review your physics, okay, for your frequency, speed of traverse, and your wavelength. It's in physics 1, I believe, or maybe 2, I don't know. Okay, so due to the phase relationship between the stylus head and the skid, the waves are distorted from the actual asperity heights. So even though we're measuring the stylus with an instrument and producing a graph, the graph is just the representation, and it can never be able to represent the real thing. Okay, so the real thing is always a little bit different from what we try to capture. Okay, just like you and your picture is actually not the same. Your picture is just a moment of your action, and also depends on the environment, like lighting, you know, light on your face, or the amount of lights on your face actually, and humidity and all sorts of that. Okay, so therefore picture cannot capture the real version of you. Same as that, even if we try to measure the surface with our surface instruments, okay, the waves what we get so usually are distorted from the actual asperity heights. Okay, you get a little bit of distortion with it, even if we try to do our best to capture the texture and the roughness of the surface. Alright, so in this figure, you can see the relationship between the stylus. So here is your little stylus, and then here is your cylindrical skid right there, and then these are your asperities. Okay? So here in A, they are in phase. In phase means like both of them are in the alley, see? So they're not on the peak. So in phases, if both of them are on the peaks, in phase, if both of them are in the alleys, okay, ravine, you can call it in phase. Okay, outer phases, one is on and one is down. One is in the alley and the other one is on the mountain. Okay, one is in the ravine and the other one is on the top of the mountain. It's out of phase. Okay, C, when you get to C, you can see there's just a little change because both of them are somewhat, you know, a little bit too in phase, and also a little bit to outer phase. Yeah, so that's how we measure the surface. So here is just trying to show you the various positions that your stylus and your skid can be able to take on the surface. Alright, the next picture right here is showing the effects of outer phase. Okay, here we can see directly as soon as you look at that. You see one is up and one is down, so that's outer phase. And it's showing you the effects of outer phase condition on the graph we produce from this measurement. So if the stylus and skid are in phase, the graph is going to show you lines, okay, like in A. If they're in phase, you will see the graph just like that. Okay. Here is because they're out of phase, so therefore you're going to get a distorted graph. So the more your instrument is out of phase between these two little parts of that instrument, the more distortion you can see in your graph. Okay. So numerical values for assessment. We're just trying to identify variables, and these are the identification of your surface characteristics and also the establishment of no ambiguous terminology. Tracer head characteristics, that's your stylus form, force support, your skid form and support, and then the traversing length, right? Traversing length is going traveling on the surface, and then you produce a graph, and you can see the traverse on the waves. Instruments characteristic, we also try to identify that. Includes your response time, cutoff lengths, the attenuation rate, display of readings. You don't have to know all of it. If you read it, okay, like a book, that's okay, and know that they're there, yeah. And the variable specimens, that's for precision, for calibration, roughness, comparison. So the nominal form of a surface is just a straight line, but the actual form of surface is a composite of all of your asperities. Okay, asperities you can see, only with the instruments, all of that. They are the variables and characteristics of your surface that we're trying to identify. Okay, arithmetic average roughness. So this roughness is also known as roughness average. We call it roughness average. So this is the beginning of the confusion of all the terms, so just go slow. Yeah, so when you're trying to learn something new, all you have to do is read little by little and then try to take it in little by little. And once again, you only have to read once, yeah, and then do the assignments just for you to kind of like a touch basis, just to know, okay, the material, not to get them by heart. Nobody is going to test you all of this. Okay, so it was also called arithmetic average, and we go by the symbol AA, and the centerline average we go by CLA. So the roughness average is arithmetic average of the absolute values, okay, of the deviations from the profile height measured from the center line along the specific sampling length. So every time we talk about the deviation, like your standard deviation, your data is always measured away from the center or the main line, same as that, okay? We have a center line, and the roughness average is we're looking at the deviations from your profile height, and that height is going to be measured from the center line. Okay, so here in this picture you can be able to see that clearly, and that's your center line. So this is your profile height. Okay, all right, so and this is just a typical roughness sampling length in the top. So you can see the roughness average, and here is your center line, and these are the deviations, okay, along that line. So that's how we study if your surface is smooth or flat or has a lot of dent or nicks or little mountains. Alright, so the lower profile is enlargement of part of that profile and has been divided into equally spaced segments. It's just showing you that we divide that, so from A all the way to P, they're all in equally divided segments. Another method to assess the surface, so we call that the root mean square roughness. So this is just a symbol for that. So it's closely related to the roughness average, which is your RA. So this method, first we square the distance, and then we average them, and then we calculate the square root, kind of similar to your standard deviation or variance. Anyway, so the resulting value is an index, okay, for surface texture comparison, and it's usually 11% higher than your RA value, which is your roughness average. So, but we don't use this anymore since 1955 because it's pretty difficult math. And in America, people don't like to do math. We always try to find, we're too smart because we always try to find the easiest way out. And by doing that, we become smarter and smarter, trying to avoid something that you don't like, so you don't have to do calculation. So that's one thing that we do a lot in America, because majority of us don't want to do math, so we always consult with the expertise in math, and then make the math easier for the common people. Okay, so that they can use a calculator, can use the software programs which are developed by the people who are really good at mathematics, algorithms, okay, logics. So, and what we use is what they have produced or made for us. Okay, so you have to be very grateful for all these scientists who have done a lot of work for us. So anyway, this is a kind of we call it specimen. It's just an instrument, okay, that you can use. So maximum peak valley roughness is another one, is R max or RT. So R max assessment is just another method to determine the distance, again, between the lines. Okay, so surface is all about the lines and the deviation from the lines. In that comes to the extreme outer and inner points on the profile. Profile is nothing but, okay, we call it the shape, but then it's actually the surface again. Okay, here you can see the exaggerated profile, exaggerated surface texture in this line. Alright, so the judgment of the observers results in different values for the same surface. So this method is popular in industrial use. Okay, we use it because it's easier for us to be able to use it. So in industry, we want to cut time, so therefore we always use something that is going to give us right away. Okay, and we can use RMAX. So 10-point height is another popular method that we use for surface metrology. So there are two assessment averages. Again, distance, we average the distance between the 5 highest peak. So you count the peaks, and then we're gonna average the distance between the 5 and pick the highest peak. Okay, here 1, 2, 3, 4, 5. Okay, so that's your 10-point height. And do your average. So that's what we're doing, the deepest valleys, okay, or 5 deepest valley. You can also choose that within the sampling length. So that's, we call the 10-point height is also another popular, because again, your mathematics is easy, yeah. Alright, the next method is your RH or HPI, is your average peak to valley roughness. So this method averages, again, the individual peak to valley heights, individual each one of them, and uses the heights between adjacent peaks and valley. Okay. Average spacing of roughness peak is a AR or AR. You can use with a little r or big R, the same thing. So this method averages the distance between the peaks without regard to their heights. This method is also known as the average wavelength of roughness peak. Okay, Swedish height of irregularities is your R or H, and this method is also known as profile job. Okay, method is kind of difficult to pronounce it, and but we usually call it R or H. Okay, so it's just a standard in Sweden and Denmark, so therefore they have their own language and term. So the method determines the distance between two parallel lines that cut the profile. Okay, most of the method is going to produce similar graph like that, and the only thing that is different is whether you are taking the peaks or taking the valleys, taking the peak and valley. Okay, so those are the differences. Alright, so bearing length ratio is your TP and other. So this method uses the same assumption as in your R and H method above. And here you can see the reference line is created through sum of the peaks. Okay, now we're using sum of the peaks. So this line is at a height from A, again, mean line. Okay, then divide the subtended length through the peaks by the sampling length to arrive at the assessment value. And again, you don't have to bother about everything if you can be able to know that there are many methods that we try to study the surface, because it is difficult to study the surface. Okay, so therefore we have too many methods, because many companies, many businesses, many institutions, okay, try many different ways to be able to study the surface. Okay, so leveling depth is your RP and others, And this method uses a symbol or ERT or RU, and the height between the highest peak and the mean line is measured. So what you have to understand right here is that surface is for academic, okay, at school, university, it's still a very important research that a lot of the schools are participating. And again, we're trying to find a way, the best method to be able to scan the surface. Yeah. Okay, waviness, height. So this method is used to assess waviness without regard to roughness by determining the peak to valley distance, okay, of the total profile within the sampling length. That's your another method, and here we're hitting the height of the waviness, okay, and you are assessing, instead of each peak and valley, we go just a waviness without regard to the roughness as your peak and valleys, and determine the peak to valley distance, okay, of the total profile within the sampling length. So it's kind of a little bit complicated. It's not a very popular method that they use, but then the research group will sometimes use this. Okay, so these are just a graph for these methods that we just studied, and they produce particular graph. So here this one is from the maximum peak to valley roughness height, and then this graph is from your Swedish, height or irregularities, and we call that the privileged on R or H, and they're a little bit different. Even if you study the same surface, sometimes you're going to get a little bit different kind of graph, because the way the method is different. This one is your 10-point height, and then that one is your bearing length ratio. Okay, look at the differences in these graphs. And then the average peak to valley. Okay, so here these are the measure point and how we calculate. And if you just look through, that's alright. And this is your leveling depth. Okay, here is your mean line, and these are your deviations from the mean line. Your average spacing of roughness peaks. Now see the direction. Instead of going up and down, we now study the direction, the distance between the peak and another peak. Okay, so you can carefully look at that. See, okay, you gotta go very slow, look, and make sure you know where you look. Okay, that's really important to become a great scholar or a good student. It's just don't just look and recognize what you're looking. Okay, so that way you know what you're looking. The same thing, so waviness sampling length, same thing here. Okay, so that's another method. This one is not that popular, but some companies still use it. Okay, other assessment methods in some industry, they develop their own methods. They don't want to use the standard methods. So in America, we can find those kind of industry, so many of them. They make their own method, and then they make it work. Okay, even if it has a lot of flaw in it, or but national standards will not recognize them, but they use it anyway. So that's because in America the power is divided, and the power is owned by the people and owned by the businesses. Okay, so therefore the government cannot be able to control these business units or the family units or the people. And so we have the power. So if you don't want to use a standard, you won't do it, and you have your own right to form your own. But the only guarding thing, your FBI, your CIA, okay, your government, is that you do no harm. Okay, meaning you won't take away other people's life, you won't injure other person, and you won't affect the health and well-being of another individual, as long as you maintain all that. Okay, laws, perform within the laws, you can do almost everything in America. Okay, nobody is gonna judge you morally or not. But again, our principle is you will not harm another individual, you will not injure another individual, You will not take away the life of another individual, and you will not disturb their health and well-being, okay, mentally and physically. So as long as you obey that, okay, and play within these rules, you can do almost everything, including in surface metrology. You can have your own methods. Businesses can have their own methods. Businesses, they do not, okay, make their own method because they're lazy. Second one is they just use a national standard, which is pretty easy because you don't have to go through a lot of math and hire researchers to develop something for you. Okay, so kind of saving their own. Some company make their own is because they have a return on investment is really high. Okay, they want to do that because by establishing their own method, they have again power and control over their businesses. Okay. Anyway, so amplitude density function is your ADF. So this method, we're getting into the amplitude property instead of the distances or deviations, okay, amplitudes. So the amplitude is you will review your wave, and amplitude is like that for each wave, okay. Probability and the amplitude density. So we're getting into probability because we're dealing with the height of the wave, okay, and the height of the wave is usually have an area underneath of that. So every time you have an area underneath of a curve, we can apply the probability principle. So the numerical value is the probability that at a given height, the profile amplitude will be within a slice height. Okay, slice height is a very minute height. Delta y, remember the y-axis and then your x-axis. So everything that is on your y-axis, okay, is called height of your sampling length. So this length is nothing but your surface length. So sampling meaning we are measuring that surface, okay, amount of this amount of length. And delta y is nothing but the surface mountains and the valleys, okay, on that surface. You can see them. They're very, very small. They're in the micro region, okay, 10 to the power -6 and lower. So anyway, so the significance of this graph is going to relate to the probability again of material along the curve. Varying length, varying curve, so BAC, another probability graph. So if you know like which one is a numerical and which one is a probability method, you're okay. There are only two probability methods. That's your ADF and BAC. Okay. When I was a student, I tried to remember the ABC and such a stupid way to try to remember. And then this is as ADF. So I tried to remember A all the way to F without the E is probability. Anyway, so this method uses the line to cut the profile instead of cutting a slice of your profile. So at the top of the peak, there's a little possibility of encountering the material. So we're talking about, imagine there's a surface, and the surface, okay, has a roughness, or your texture is definitely not totally flat. So in that case, you can be able to have some sort of a profile, okay, and we are talking about the little material that can be up or down on that surface. So as the line is lower, the probability of encountering material increases. Skewness is, every time we talked about the probability, we always think about the skewness, and it looks like this on the graph representation. So this method measures the symmetry, okay, of the profile and revolves about a mean line and can be expressed numerically. So here you can see it's totally left skewed and this one is totally right skewed. Okay. Then we will get into the graph. So here you will see the amplitude density function, which is your ADF graph, looks like that, pretty rough, huh? And your variant area curve, okay, your BAC looks like this. Okay. And you can see the differences right there. So here we're going with the delta y, yeah, and here without the delta y. Kurtosis is like this. So this term means the quality of pickedness. Okay, so pickedness is nothing but I usually go without silence ed. I just call it like peakness. So what we're trying to say is the height of this peak. Okay, and we're dealing with the quality of these little peaks right there, and we call it kurtosis. And if it applied to the ADF, the first method, it would measure the sharpness. So since we're dealing with the peak, we are dealing with the sharpness as well. Yeah. So when you imagine the surface, some of the point on that surface, okay, we will measure with the kurtosis to measure the sharpness of that surface. Okay, autocorrelation function is called ACF. Right, so this method can measure the similarity between two identical but laterally shifted profiles with this method. So the graph of this method produce make it easier to distinguish characteristics of surfaces formed by different methods, right? So it's good for comparison. So ACF, surface study method. Okay, what we do is we're looking at the similarity again between the two identical. They are identical, but they are laterally shifted profiles. Yeah. Alright, so next graph, here's your relationship of amplitude sensitive parameters. So those are your assessment value, that's your mean line, those are your deviations. Okay, that's your ADF and then your BAC. Okay, we're just looking at in different ways for a particular surface. Then here is, you can see your skewness. So this graph is kind of like a side view. So you can imagine to flip it back and you can be able to see the skewness right there. Okay, so that's your right, and then that's your left, and then this is kind of a left skew. Yeah. So mean skew is less than 0. This about equal to 0, even though there's a little bit of tiny bitty bit right here. Could they take it as oh okay, that's no skew, and here is on this side. Okay. Right, the surface texture specimen is just an instrument, okay, even if we call that specimen, it's just an instrument for surface metrology. So there are two types of surface texture specimens. The first one is your precision reference specimen, and that's for instrument calibration, and the roughness comparison specimen is your direct visual and the tactile comparison. So this is your roughness comparison specimen, okay. This is your precision reference specimen. Okay, surface texture specimen. So here, this is your precision reference specimen box right there. And for an example from this mid-tutorial American corporation company. So precision reference specimen is your precision reference specimen is just a tool, okay, for surface texture to study the surface texture, and it is used only for field calibration. So 3 primary characteristics are calibrated with this method. So they are your roughness height, your stylus checking your stylus on your instrument, and then your profile height. Okay, profile is again the deviations, right, of your surface. So you want to check your surface height is your profile height, and we use this roughness comparison specimen. So this method is visual. This method is totally tactile, and it is used to make roughness comparison. So pilot specimens is a method again we use. Okay, it is used as basis for comparison again using actual production parts selected with the desired surface finishes. And this method makes it easy to compare parts, right, to those that have already been thoroughly tested. So they're all again instruments to measure your surface texture. And if you can get the name, and if you look at it and you realize, oh, precision reference specimen is surface texture specimen, I will be very happy. Okay, surface evaluation and other methods. So the assessment of surface texture is the only contact method in general use. So here in this picture, you can see a portable, right, surface roughness measurement instrument for shop floor use. You can take it with you in your pocket and study everything that you need to study. It's just a tool right here. So optical types of instruments are used for non-contact. Optics are usually non-contact methods. So other non-contact methods use on your phenomena for your physics, your optics, and then your electronics. So all non-contact methods do roughness assessment, not waviness. So they do not provide graphical record. So these methods provide the most direct comparison needed to control critical surfaces. So they are in use in some departments of defense specifications. Okay? So again, for surface evaluation, we have a contact and we have a non-contact method. Okay? And try to pay attention on which ones are contact and which ones are non-contact. So if I say the optic type, then you should be able to know that's a non-contact method. Roundness. So surface metrology is important for roundness control, okay, only in, again, spheres. So roundness is a geometric aspect of surface metrology, and roundness in bearing is often overlooked in routine work. Okay, we don't really, sometimes we overlook some of the stuff when you study the surface because we feel like it's not very important, but actually roundness is a geometric aspect of surface metrology and is actually important. Okay, and we really have a roundness control in spheres, especially in spheres. The lobes and the V-block method, the waviness on flat parts is referred to as lobes on cylindrical parts in this method. And the method, this method look at the higher frequency asperities on round parts, and they are as much the same way we assess them on the flat parts. So surface datum instruments are used, but to detect lobes, and we use true datum instruments. So roughness does not affect the dimensions of a part at all, and lobes regularly they affect perceived dimensions only. So here you can see the lobes, okay, on the cylindrical parts right there. So here 1, 2, 3, 4, and here 1, 2, 3, okay, lobes right there. And we usually use the caliper type measurement, and we call the AA or BB, and because they can provide enough data to calculate the height of the lobes. Okay, little heights right there, right here. But unfortunately, it's nearly impossible to determine the number using only, okay, diametral measurements. So diameter is nothing but from here to here. Okay, so you definitely know the diameter of the cylinder right there. But as we move, you're going to come into the lobe area. So at that point, you're going to see the change in that diameter. Okay, that's how we measure the height. So you're going to have difference between your original cylindrical diameter and then the increase in diameter. Okay, so when you minus that, you're going to get this height. Okay, so that's how we measure the surface lobes. Okay, V block. So here V-block method is they're adopted to improve the measurement. Okay, V-block is nothing but this little block right there that looks like a V shape. So they're usually used with comparator as an easy method of measurement, and a better instrumentation must be used to determine the number, okay, of lobes. So true datum stylus can be used instead of comparator. Okay, here is your little stylus right there. So we have a datum instruments right up there, true datum instruments right up there with your stylus. It can be used instead of comparator and analyze the graph, yeah, produced as the part is rotated. So you're going to rotate this one, and the stylus is going to run or travel on that surface, and then we use this little V block down there, okay, to support the part that we're trying to measure. the polar charts. There's another method. The stylus instruments that produce polar charts are more commonly and widely used. And you can see right here, a polar chart instrument. So this method is a true datum instrument, and it consists of a precision spindle, okay, to control the path of the stylus head, and a table, okay, to align the workpiece with a spindle. So here you can definitely see the table and the spindle to control that stylus. So there's no skid, so stylus can pick up all departures from the circular reference part. So after setting the sensitivity, the instrument will record the datum, okay, for the desired surface feature on a polar graph. The polar chart method. So the advantage of polar graph is shown here in figure 1321. So when a proper V block is used for a 5-lobe part, so you're going to put that part right at the V block support, and then you're going to measure with the stylus by rolling that thing, okay, on the block. And we have this graph A. So graph A shows 5 lobes, okay, with 26 shorter asperities. So you have blah blah blah. If you count it, there are 26 of them, and they are totally superimposed. So if we use a V block with out of phase cancellation, remember the out of phase, okay, this skit and your stylus out of phase, because one is on top and the other one is down. So we get graph B. Okay, after cancellation we get graph B. So look at that, how clean your graph is. So still revealing the lobes, okay, but at reduced height. In graph C, okay, which is this little one, is easier to comprehend the lobes. Okay, you have your lobes and then your asperity. Yeah? The lobes are right there. Okay, you can see 1 and then 2 and then 3 and then 4 and then 5. Asperities are a little wiggly one. Okay, weird stuff all around. Alright, the polar chart method continues. So polar graphs often, okay, have concave profiles. So here we have concave profiles. Your concave and convex. Make sure you review your physics 1 or 2 as shown in figure 1322 because of the radial magnification is so great. So in A, the departure is shown as x, okay, right here. So that's your departure. And here you can see the perfect circle, and you can see the profile, which is your part profile, right there. And there's a difference right there. So if we double the radial magnification, the departure is represented in B. Okay, now we have x2. See how it goes. And then the magnification, we're gonna quadruple. So you can see better, yeah? Not much, can see a little more, a little better. So now the shape that we see at 1x, okay, is actually this, yeah? In higher magnification. So that's at 4x. And the side appears, okay, and you can see that like a hexagon. Now we're gonna zoom in to all the way to 8x. Okay, so 8th power right there. So your magnification is really high, and now you can see the true surface. See? And it's completely concave profile. So what we see outside with our eyes is not their reality. Okay, we have to go into a very, very minute world for us to be able to see what's truly going on. Again, only at that level. If we have a more powerful, okay, magnification and go down 10x or 16x or 64x even, you're gonna see a different reality. So therefore, try to get a habit. Okay, you're a university student now, studying science, engineering, mathematics, and technology. So therefore, what you have to understand about yourself is we have many different worlds, okay, and that's going on with the level, again, level of your vision, level of your sensitivity, level. Okay, so life is, there's so many lives, billions and billions and gazillions of life at every level, okay, of existence. And do not forget that. So don't think like we're the only people living in the world. No, there's so many lives that you can't count. Okay, so the tolerance for roundness is found in A and SI, and your standard is Y 14.5, dimensioning and tolerancing. Okay, that's just a review from the earlier chapter. Alright, surface assessment, that's of lost slate. This is trying to tell you the best way to become efficient in surface metrology is to use a variety of instruments. We do this, we do that, we develop different instruments, and I try to measure again. The more we measure the surface, okay, the more interesting it is. And again, we go all the way down and come to realize everything in the world is not actually connected. They seem to be connected, okay, but they're not. And that, I don't know how to call that, the paradox. Yeah, okay, paradox is our nature. Okay, things seems to be one way, but it's also happening in the other way around, completely opposite way around. So it's going to blow your mind the more you study deeper and deeper into the science. Science is nothing but we're trying to study who we are, where we are. Okay, what are we doing? What do we have here? And what else do we have? Okay, can we be able to get there? Why don't we try that? Because that's what we're trying to do again and again and again and again. Yeah. Okay, so that's it for today for this chapter.